Hello students, welcome back. Now we have almost finished your syllabus. I have just left with three of small chapters. One of the chapter is diffraction of light. Now after interference, that is one of the property of light. We will study about diffraction of light, which is the another property of light. Now to understand diffraction, it is another name, or what we can call it is bending of light. Okay. Now, if an opaque obstacle or aperture is placed between a light source and a screen, suppose we have a light source, a bulb, suppose for example we have a bulb and there is darkness in the room and small slit and the screen. Now what we can see is from this small slit the light will enter and we can see some sort of illumination in the screen. This shows that light travels approximately in straight line. If, however, the size of the obstacle or aperture is small, if this slit is also known as aperture, if it is small, there is a departure from straight line propagation and the light bends around the corner of the obstacle. So, now if this is a bulb, first of all what happens is a plane wavefront will travel, but when it reaches the slit portion, this is the aperture portion, when it reaches this portion the light travels in a straight line, but what happens over here, if the hole is quite small, then the light will bend and this type of the wave will travel. This is spherical waves and this will be seen in the screen. So what we can see is the light which is traveling straight over here, it bends around the corner, it bends at these edges. Over here it bends at the edges. So the bending of light around the corners of the obstacle or aperture is called diffraction of light. This is a characteristic of wave motion. A plane wavefront is advancing towards a small aperture and in a cardboard, most of the part of the wavefront is reflected back. From this cardboard, most of the wavefront is reflected back from the cardboard and only a small portion in the middle passes through the aperture. As the middle portion of the wavefront reaches the aperture, according to Huygens principle, the aperture acts as a new wave source. So this aperture acts as a new wave source and from there, spherical wavefront emerges from the aperture and advances with the same speed as the speed of plane wavefront approaching the aperture. We know that in a homogeneous medium, the wavefront is always perpendicular to the direction of propagation. That means if the medium is homogeneous or same medium, the light will not, wavelength of the light will not change, even the speed will not change. It will move in the same direction or perpendicular direction. Hence, the wave emerging from the aperture move not only straight but also bend. This is a diffraction of waves. Now, diffraction is of two types. One is Fraunhofer diffraction and other one is Fresnel's diffraction. Now, Fresnel's diffraction has been removed from the syllabus, so we are left with Fraunhofer diffraction. Okay. The next topic or a type of diffraction is Fraunhofer's diffraction. Now to see Fraunhofer's diffraction, one experiment can be done that is due to a single slit. We scratch a fine slit by means of a razor blade on a biology slide painted black on one side. So if we have a slide painted black, what we do is we take small scratches over here. We see this through a vertical filament of the lighted bulb. So we see this through a filament bulb. Okay, we can use a filament bulb to see the illumination. Now we keep a this slide in front of this. We observe a central bright band having the both sides narrower, alternatively dark and bright bands are decreasing intensity. So I'll just show you the diagram which is there in the book. Now, such a type of a pattern is seen on the screen. Now, this central one is central bright fringe. It is totally bright, a very slightly of gap. Now, the intensity over here is maximum. Now, intensity of bright fringe is decreasing. It becomes lesser and lesser as we move on further. So, in a diffraction pattern, the central fringe of brightness is maximum. Now the intensity further decreases. So this is a type of pattern which we see in a Fraunhofer diffraction. Now, finer the slit, the more fine the slit we make, what we see is a wider diffraction pattern. If light travels strictly in a straight line, then the image of the slit would have been a fine, bright line. The formation of the diffraction pattern indicates that when light passes through the slit, it bends at the edges of the slit. It is due to the diffraction of light that the images of stars in the telescope do not appear as sharp points but appear as diffused spots. If you wrap a colored cell phone paper on a lamp, then the diffraction pattern is also the same color. It is seen that the diffraction pattern formed by the red cellophane, it's cellophane or red, spreads more than the diffraction formed by a blue light. From this, it is concluded that the wavelength of red light is longer than the wavelength of blue light. So we'll do a geometrical arrangement and a derivation for this Fraunhofer diffraction as well. So the diagram is given in the book itself. I'll not draw another diagram. I'll just show you the same diagram. Okay. Now, the geometrical arrangement to observe Fraunhofer diffraction by a narrow slit is shown. A parallel beam of monochromatic light of wavelength lambda is incident normally upon a narrow slit of wave. There is a slit of width AB which is equals to E. This placed perpendicular to the plane of the page, which is placed perpendicular means the slit is placed like this. Okay, if I think I'll show you. The slit is placed like this to the plane of the paper, perpendicular to the page of the paper. The diffracted light is focused on a convex lens L on a screen XY in a plane focal plane of the lens. The diffraction pattern is described above is shown over here. Suppose the slit with AB is made up of large number of parts. If this AB is made of large number of parts, say twice n. Okay, the derivation part I'll just write in the paper. So for Fraunhofer diffraction, if AB is made up of a part that is say 2n. Accordingly to Huygens principle, each part that is twice n is the source of secondary wavelets. All wavelets originating from these parts are in the same phase. So this light which is coming will be in the same phase because there is only a single slit. There is no double slit like in the case of interference. Now those wavelets which proceed in the same direction as the incident light are focused at a point O. Since all of them are in phase, they reinforce one another and produce a central bright band at O. The bright band which I've seen over here, this kind of a bright band is formed at the center, that is O. This band is called the principal maximum. This point is known as the principal maximum. Most of the incident light is concentrated in the principal maximum. The wavelets diffracted through an angle theta are focused at point P. So, at an angle theta, another ray of light is traveling, which is meeting at point P. These wavelets start from the various part of the slit AB. in the same phase, but they reach the point P in different phase. So what we can see is the light reaching at O, all the ray of light are in same phase, but the light reaching at P, this ray of light and this ray of light are in different phase, because this one is traveling a shorter distance, whereas this one is traveling a longer distance. The wavelets diffracted through an angle theta are focused at P. Those wavelets start from the various part of the slit and reach P at different phases. So what we can do is, we can draw a perpendicular over here such that distance AP equals to distance KP. So just to make the distance equal, we draw a perpendicular. So what we can do is, we can draw a perpendicular just like in the diagram. Let AK be perpendicular drawn over BK. So AK is perpendicular drawn over BK. The optical path from the plane AK to the point P are equal. So the light reaching from this point to this point are equal. So from this line to this point, the distance is equal. We have just cut that perpendicular to make the distance from A to P equal and K to P equal. The path difference between the wavelets from point A and B of slit is, this is the path difference. Between these two rays, the path difference is BK. So we are just writing for first dark fringe. Okay, for first dark fringe, as I have told you, the light reaching over here are in different phase. So if they are in different phase, they will form a dark fringe. So for first dark fringe, phase difference is BK. Okay, so we can consider the phase difference as lambda. Okay, let us now divide the slit AB into two halves, each containing n wavelets. So this AB can be divided into two halves and each contains n number of wavelets. The wavelets from the corresponding points in each half have a path of lambda by 2, because wavelets interfere with n plus 1, 2 interference with n plus 2, and so on. So what we can consider is, we are considering BK is equals to this distance, BK is equals to lambda. We consider this as one single wave. And what we know is BK is this side BK. If you consider this as a right angle triangle, BK is AB sine theta. So from in a simpler way, what I can do is, from triangle ABBK, sine theta is equals to, or from triangle BAK, from this triangle over here, we can consider sine theta is equals to BK by AB. So sine theta is BK by AB, which is equals to BK by AB is E, or BK is equals to E sine theta. And what we know, BK is lambda. So E sine theta is lambda, or plus minus m lambda, where m is integer, which can be 1, 2, 3, etc. Now since plus minus signs mean that dark fringes are formed on the both sides of the principal maximum at O. So from O, this point O, dark fringe can be formed on positive side as well as negative side. That is what this plus minus over here, indicates. This is for the first dark fringe. Now Now what we know is, obviously some light reaches between consecutive minima where weak maxima are formed. So light reaches each and every point. Minima is where dark fringes are formed, and where maxima is where bright fringes are formed. These are the points on the screen corresponding to which the path difference between the secondary wavelets originates from point A and B of the slit AB. So if I draw a wave diagram of this one, then the wave diagram will look somewhat like this. In the center we have a center maximum. Okay, this point is O. This side is the intensity. Then the intensity of the light decreases like this. Okay, on both the side the intensity of the light decreases. This is the principal maximum. This is the minimum, which is at lambda by E. This is minus lambda by E. The value of this one is given from here. Okay, the lambda by E value is given from the previous derivation. That is, okay, the equation was E sine theta is equals to plus minus m lambda. So from here, sine theta is lambda by E. So from here we get the value of sine theta, or the angle. Now first one is lambda by E, then second will be twice lambda by E. Okay, and so on. Over here will be minus twice lambda by E. Now for the first secondary maximum, okay, the second one will be for, or we can write mth secondary maximum. That is, secondary maximum means this wave over here. For secondary maximum, m will be, it is between lambda has got, okay, I'll tell you again, lambda has got maximum, then another maximum will be at twice lambda. Over here it's lambda, then comes twice lambda, then comes thrice lambda. So in the middle comes 3 lambda by 2. This point will be 5 lambda by 2. This is where the minimum occurs. So for secondary maximum, your E sine theta will be 2m plus 1 lambda by 2. Suppose if we keep m at first wave, okay, for the first secondary maximum, then this equation becomes E sine theta is equals to 2 into 1 plus 1 will be 3 lambda by 2. This is where we get the secondary maximum. Now the angular width of the central maximum. For the angular width of the central maximum means the angular width of the central maximum is the position between the first minimum on the two sides of the central maximum. So angular width means this angular width. So for this one, for angular width, sine theta is equals to lambda by E, wavelength divided by E, that is the distance of the slit. So from here theta will be sine inverse lambda by E. So the angular width over here, if this distance is theta, this distance is also theta, then angular width will be 2 theta is equals to 2 sine inverse lambda by E. This is the angular width of the central maximum. Now what happens if the slit is made narrower? If the slit is narrower, if E is small, slit narrower means if E is small. The first minimum on the either side of the central maximum occurs in the direction of theta. Okay, that is what happens. Where E sine theta will be plus minus lambda. So if E is very small, the theta increases. Okay, this theta increases, which means that the central maximum becomes wider. If the theta is bigger, okay, if E becomes smaller, then theta becomes bigger. Okay, if slit becomes smaller, if E becomes smaller, theta becomes bigger. That is what happens if the slit is narrower. When the slit width is as small as wavelength, when E becomes equals to lambda, the first minimum occurs at 90 degree. This minimum occurs at 90 degree, which means the central maximum fills the whole space. Now, important points to remember is diffraction is exhibited both by light and sound waves. Transverse and longitudinal waves both show diffraction. It does not verify the nature of light, whether it is transverse or longitudinal. Diffraction takes place when diffracting obstacle is of order of wave. Now there is difference between diffraction and interference. Please just go through it. With that, the chapter is over. There's not much in this chapter. Okay, just a diffraction pattern and few equations. The derivation part is also not there. Just remember the equations, diffraction pattern, and the difference between diffraction and interference. Okay, that's much for today. Thank you.